undesirable outputs models. So why do we need undesirable outputs and so on? That's what we'll cover today. If you have a bad output, what do you do? Okay, the simple thing is to ignore them, which is what most economic analysis does. But if you don't, how do you deal with them? So we look at alternative methods, and we look at also how you build a frontier. So this will be an introductory lecture. So when we say undesirable outputs or bad outputs, well, these are outputs that are jointly produced with desirable outputs. So normally all the stuff we want to produce is desirable, it's marketable, but we can't avoid also producing bad outputs like pollution. So if you are producing electricity, then you will be producing carbon dioxide and sulfur dioxide at the same time, or greenhouse gases. In most economic analysis, until the 1980s at least, these undesirable outputs were just ignored. So you ignore them. That's how it was. Just like all economic analysis. So the environment is external to economic analysis. That's how it was. It's only in the last 50 years where we have had changes so that we take into account what we do with the environment. And this is no exception. If you are doing productivity measurement in the 70s, 80s, 90s, you go and do your productivity measurement as if undesirable outputs don't exist. So you could have an industry which is generating a lot of pollution. You look at the stuff that it uses and the stuff that it sells. That's it. And you ignore the rest. But what's the problem with that? Well, first, you are ignoring something that has an effect on welfare and the environment. So that's a problem. But that's not the only problem, because sometimes the polluters will be spending resources to clean up or to reduce pollution. But the cost of the cleanup might be counted as an input because they are hiring people. So sometimes you don't know what proportion of the labor force is engaged in pollution reduction and what percentage is in production, how much of the management's time is spent on cleanup or dedicated to managing cleanup, how much of the capital in the industry or in the plant or in the factory or the company is spent on cleaning up resources or managing environmental effects. So what that means is, while the benefits of pollution reduction are ignored, the costs are counted. Now, I know this is the exact opposite of what people tend to think. People, when they think of bad outputs, they think, oh, these companies are polluting and we are not counting the damage they are doing. So they look good and we are ignoring these undesirable outputs, and that makes them look good. Of course, it does. But when you are dealing with productivity measurement, you are also dealing with how things are changing over time. So if you take changes over time, and if the companies are cleaning up, actually they are getting better, but you cannot notice that they are getting better because their resources are being spent on pollution reduction. So even if you measure that they are improving in productivity, you underestimate the productivity measurement. Worse, you could have two different companies or two different provinces or countries. One country is investing in pollution reduction. The other one is doing business as usual. Now, when you compare productivity, you will turn around and say that the country that's doing environmental cleanup is actually lagging in productivity. And there was a lot of literature in economics just dealing with this. Has the environmental regulation or the environmental regulations that were introduced into countries, especially North America in the 1970s, have they reduced productivity growth? And there were many studies on this because there was supposed to be a productivity slowdown, and that productivity slowdown was never explained fully. So this productivity slowdown, you probably never heard of it, occurred sometime in the 1970s. So American productivity just dropped in the 70s, and people were trying to explain why. Why did productivity just slump? Well, what happened in the 70s? Many things happened in the 70s. One, a lot of women joined the labor force in the late 60s and 70s. So one explanation was, well, the labor force was now in terms of skills, because this new component in the labor force was less skilled, that dragged down productivity. That was one. Some people thought, well, it must have had to do with environmental regulation, because in the 70s, there were stricter environmental regulations. So that must have messed things up and made companies look less productive, because we don't count the benefits of environmental pollution, but we count the cost. A third explanation that was given, well, just the three I remember, there could have been more, was that in the 70s, what happened? What was the major event around the world in the 70s? Does anyone know, other than environmental movement?
There was the oil crisis in Vietnam.
There was the oil crisis in Vietnam. So what did the oil crisis do to the economies? The price of oil shoot up, right? And that was when OPEC was created in the 70s, in 1973, there was an oil crisis. And in some countries, the old capital equipment that was using a lot of energy had to be scrapped. So they had to come up with newer, more efficient production processes, and that meant bad for productivity because they had to get rid of a lot of capital. So when you think of pollution abatement and bad outputs, don't think that, counting pollution would make companies look they are underperforming. It could be the other way. If they are improving their management of the environment by reducing pollution, ignoring pollution actually means that the companies look worse than they are because over time they are investing a lot. And that has happened in some countries, not all, but in some industries that have had to invest quite a bit because there was no way they could continue the way they were producing with the level of water pollution they was causing. So good example, I will talk about this later, is the Canadian pulp and paper industry. Okay, it's a massive industry and it was the number one source of water pollution in Canada. So the effect of ignoring productivity measurement could, in short, could make companies look worse, not the other way around. And that's what I was saying. Of course, companies do pollute, and that means they cause damage to the environment. But if they are improving that, and if you don't take into account that improvement, they look bad over time. Well, they don't look as good as they could look over time. So the problems that we would have are, one, our estimates of relative efficiency could be distorted, and our estimates of productivity change could also be affected because we would underestimate or overestimate. And these effects could be significant, and the shadow price of bad outputs would also remain unknown. So that should be a separate point. So we don't know what it would cost to reduce pollution. We don't know what the real relative efficiency is, and we don't know what the real productivity change is. So we have undesirable outputs that have been ignored. So it's only after the 70s that we have been interested in considering the way we do economic analysis. So you might have heard of the phrase triple bottom line. So these days, when you think of economic analysis, you have to think of the economic, okay, and the social and the environmental. So you could say this is financial, but that's the triple bottom line. So everything, if you are thinking of big projects, you need to be both economically, socially, and environmentally responsible. And before that, we didn't have the motivation to do that. So it was fine to ignore environmental effects. But the other thing was we didn't have the methods. So until the 70s, mostly people thought about production functions, and production functions meant, well, there was only one output. So whatever you had to do, you had to make sure you aggregate things, but then bad and good outputs cannot be aggregated. One is bad, the other is good. You cannot use monetary values because you don't have monetary values for pollution and so on. And that was a problem. In terms of data problems, we also had, what's wrong with this PowerPoint? I've got a few typos in there. We also had data problems. There was no pollution data. So if there is no pollution data, because there was no interest in collecting pollution data, then how are you going to do any economic analysis? So there's no way you could get even started. But that all changed. So in the last 30 years, there has been more and more research. And some of the first people to do research accounting for environmental effects were in the 70s and 80s. That's 1983. And then there were some more, Farr and Groskopf and so on, in the late 80s. And then in the 90s, there was more and more interest. And the methods that were available had been around since 1953, but were never used. So we'll look at input distance functions. Sometimes what happens is somebody creates a method or a technique. It sits there because people don't appreciate it enough or people don't see a purpose for it. And if it's not taught, then it's never known widely. And that's what happened with last week. We were talking about Shepard's lemma, about cost functions. Well, in the same book from 1953, he had an idea of what's called the input distance function, and that was dual to the cost function. But that wasn't used until the late 80s when Farr and Roscoff came and began popularizing the method. So what's our interest here? Well, several. One is we want to measure performance in ways that are more balanced. So we want to know if you account for environmental effects, what's efficiency, what's productivity change, and who is better than who, and so on. And the other thing is we are interested in shadow prices. So we want to know the cost of pollution reduction. So a few years ago, well, not a few years ago, 14 years ago or 13 years ago, when Kevin Rudd came to power, they were going to introduce what's called the emission trading system for carbon in Australia. And the first thing that had to be estimated was the cost of carbon. How much does it pay cost per ton to reduce carbon in Australia? And what do you think the estimates were? 5, 10, 20, 30?
$7 or $14?
7 or 14, okay. Any other guesses or estimates? Well, I think the government thought it would be 23 or something in the 20s, okay, because there was no market. So you only rely on estimates, and there were consultants trying to estimate the cost and so on. Actually, there is a paper by one of my PhD students, Kai Tang, from a few years ago, where we did work on carbon abatement estimates for Western Australian farms, broadacre farm, WA, and he used two things. One is he used distance functions, and the other thing is he used my whole farm model that I had built for Katanning, the Katanning region, and estimated cost of carbon abatement in 2 ways. And what he got is actually close to this. And that was a good surprise, but there was no guarantee that your estimates could be around that, but that's what the government had in mind. So when you do work in this area, your motivation could be coming up with shadow prices. So we have done work with Chambo also on China. It's in the folder, estimating the cost of carbon abatement for Chinese provinces. And this is a major motivation. So it's not productivity measurement only, it's also knowing the cost of pollution reduction so that you can inform policy. So if you know the cost of pollution reduction, then you have a good idea of what the cost on companies or on societies would be of reducing or cleaning up the pollution. So that was the plan, 23, but I think the European Union has an emission trading scheme, and that comes close to what you were saying, that's lower. So how did economists try to study this? First, of course, they would go for the things they know. What do economists know? They know cost functions. So if I am an economist and I am not familiar with these new methods or distance functions, what do I want to do? Well, I want to use my cost function, but this time what I'm going to do is my cost function is going to have a bad output. And the cost function is flexible. Why? Because it doesn't limit you in terms of the number or type of outputs you can have. You can have bad outputs, you can have good outputs. Maybe the monotonicity requirement is different. In a normal cost function, if you want more output, then you would expect the cost to go up. But for pollution, what does it mean? Well, if you want less pollution, maybe the cost function would go up. So the monotonicity requirement would be the opposite, because reducing pollution costs resources. Beyond that, in terms of using a cost function, you could use a translog, you could use both bad and good outputs and go doing business as usual. So a cost function was a natural way to go. They cannot use a profit function, of course, because a profit function requires prices, and they don't have prices for bad outputs. So, but the cost function was feasible. But as we know, using cost functions requires two things. One is you have to assume that cost minimization is objective, and that works fine in some cases, but in some cases, as we were saying last week, it doesn't. But the second thing is you have to also have the prices, and those prices might not be available, or if you have them, they probably are not high quality. And in those cases, you are limited, because even if you had data on good and bad output and also inputs, you cannot use the cost function. So what was really needed to grow the literature was primal methods such as DA and distance functions. So DA is very flexible, as we have seen, and you can also include bad outputs in it. And distance functions are a generalization of the production function. They are primal. They don't need assumptions about maximizing behavior or minimizing behavior, and you can just include multiple outputs very easily, like in DA. Except when we say distance functions here, we are talking about parametric distance functions, but there is another interpretation of distance functions as a measure of inefficiency. So I will explain what the distinction is later, but these methods being available, one of them having been around from the 1950s to Shepard 1953, meant that there were readily available methods that were easy to implement to do the analysis. So this is what helped in terms of growing the literature. So what are distance functions? How do we include undesirable outputs with distance functions? So that's a new thing. DA we have covered, except in terms of the disposability assumptions. So when you take the production function, you have y as a function of inputs. So you, as I said, you can have only one output, or you have to aggregate your outputs into one. But when you have a distance function, no problem, you can have multiple outputs. So that's a distance function. Now, there is no left-hand side here, right? So all the variables are inside the function. And the result is the distance function value is going to be the result. And that distance measures how far away or how close an input-output vector is to the frontier. And if you are on the frontier, then you are efficient, then the distance function value will take a certain value, which could be 0 or 1. I will explain why 0 and 1 are equal. It's for different distance functions. For directional distance function, and if it's input or output distance function, then it's 1. Okay. So basically what it means is the distance function is a measure of how far you are from the frontier, as measured in terms of absolute distance or in terms of proportional distance. And if it's measured in terms of absolute distance, it's 0 when it's efficient. And if it's in terms of proportional distance, it's 1 when it's efficient. So we'll come back to this detail, but the main things to remember are distance functions. You can have multiple outputs. They are primal, so they are like the production function, and they tell you whether you are on the frontier or not, if it's 0 or 1. And if it's different from this, then you are inefficient. And they also tell you if something is feasible or infeasible. We'll come back to that. Okay, so in maths, distance is a well-defined concept. We know what distance is. So if you are given two vectors, you know how to calculate the distance. What happens, so if I have x and y here, and if I give you a point A and I give you a point B, you know what the distance between these two is. It's going to be, you know how to calculate that. You take the difference in x value, square them, plus the difference in y value, square them, and take the square root. So that's the triangle stuff. But what is the distance if we have x and y, and this is our production function, and I have a point here? What's the distance between A and the production frontier? What do you think is the distance? Is there a unique distance here? There isn't, right? Because there is so many different ways you could measure the distance, okay? And that's what brings us to the concept of the different distance functions. So if I have this, if I measure distance along the blue arrow, what am I doing? Well, this is my input, that's my output. So if I am going along the blue arrow, I am thinking in terms of reductions in output. That's one way to measure distance. So this is input oriented. But if I measure along the red arrow, that's another way, that's output oriented. And if I am on the green, what's happening? It's both input and output oriented, because what I am doing there is I am thinking in terms of reducing input and increasing output. So this is a combined direction. So this is both input and output. And the only issue here is there is no unique direction that combines both input and output. Why didn't I have another one here? Why couldn't I go here? So this is unique, that is unique. So if you are going with output oriented or input oriented, it's unique. But in terms of how you would measure distance using a directional, this is what's called directional vector, depends on the direction you choose. So I mentioned we could measure distance, but there are two ways to measure distance. So if I think of the blue arrow, in absolute terms, the distance between E and the frontier, But if I am interested in a proportional measure of distance, I can also think in terms of, well, by how much could I have shrunk this? In proportional terms, I can express the same distance. And it's the same with the output oriented. So what we have, we'll come back to this later, is this idea of distance in terms of deflating inputs. And this is called the input distance function, the blue line. Another one is in terms of enhancing or inflating output, which is the output distance function, the red one. These are called radial. They are called radial because they are about scaling. So it's in terms of moving your input vector closer to the origin. That's why they are called radial. Or your output vector away from the origin, which is again along a ray through the origin, radial. But if we think of dealing with both inputs and outputs simultaneously, by adding to the good things, such as output, but subtracting from the bad things, such as inputs and bad outputs, then we have a directional distance function. So this simple diagram captures all that. So if you want to measure how far you are from a frontier, several different ways to do it, and three major ways. One is an input-oriented, based on a proportional reduction in inputs, and output-oriented, which is based on a proportional increase in output vector, or a directional one, which is based on a reduction in the input vector along a certain direction, like the green line here, and at the same time, an increase in the output vector through addition along the same direction. So three different ways. The input-oriented and the output-oriented ones, or the input distance and the output distance function values, have an easy interpretation. Are easy because if you reduce your inputs by a certain proportion, then it's the same thing as reducing cost by the same proportion. It's the same with output-oriented. If you increase your outputs by a certain proportion, then it means you are increasing your revenue by the same proportion. The directional distance function is a different story. Directional distance function is more linked to profit because, as you can see there, you are adding to output and reducing from input. So it's similar to looking at the difference between revenue and cost, and that's more along the lines of profit enhancement. So these are the basics. So far, we haven't had to deal with this because for a moment we mentioned, well, if you have a production function, you could have an input-oriented measure or an output-oriented measure. Well, we are expanding this to a more general case where we can have any number of outputs, and some of them could be bad outputs and inputs and so on, and we won't have a general method.
When we're defining directional distance function, can we say that we will have a single pair or unique pair for each observation in the dataset?
Okay, so when we are talking about pairs, that's more about DA. And in that sense, what we would find there is not different from any of the usual efficiency measures we are looking at. So if I have a DA frontier, so if I take this is my DA frontier. So what's going to happen here, and it's the VRS version. Let's call this A, B, C, D, and let's call this E, F, G, H, I. So if I take point E, now who is the peer for point E?
B and C. Yeah, B or probably B or A or B.
First, let's talk about, we are looking at point E. Let's talk about the output-oriented measure. If it's the output-oriented, I am
B and C.
I'm thinking in terms of going this way. Well, I should not confuse things. I have to be consistent. Red, okay? Peers are
B and C.
B and C. If I have an input-oriented,
A and B.
peers are A and B. If I have a directional, now, which way am I going? Well, it depends on the vector I pick. So the vector I pick, if it goes this way, it will be B and C. If it goes straight here, it will be only B. If it goes that way, okay, so if I put more weight on output reduction relative to input reduction, I should say that the other way. If I put more weight on output enhancement relative to input reduction, I am likely to end up here. If I put more weight on input reduction at the expense of output enhancement, I am more likely to end up somewhere in here, okay? So the peers could be B and C, A and B, or B, depending on direction chosen. Okay, so with directional distance function, how you measure distance will depend on the direction you take.
So that direction will be same for each observation, for example, for F, G, H, and I.
You should stick with the same direction. So some people have this crazy idea of that doesn't make sense. Direction has to stay the same. Otherwise, it's like mixing apples and oranges. I cannot measure the distance of this observation using a direction like that and measure the distance of that using another direction. And this one using another direction. That doesn't make sense. If you want them to be comparable, you have to have the same yardstick.
So peer vector will be same for each.
Well, now careful. So let's go back here. I don't need to draw anything. So even if I maintain the same direction, let me just get rid of the mess I created there. Even if I choose a direction called, we write the direction as 1 for output and -1. So it means basically my direction is 135 degrees, okay? So I increase outputs and decrease outputs in that direction. Then, so this is going to go this way, this is going to go this way, but where you land, the direction is the same. They are parallel, but where you land on the frontier determines who is your peer. For F, the peers are A and B. For G, it's B and C. And for I, it's D, and for H, it's C and D. So the same direction doesn't mean the same peers because you end up on a different frontier.
Okay, thank you.
You're welcome. So production possibility set is used as the basis to define many things we have seen by now. Production possibility set is the one that would let you know what feasible input-output combinations you have. So if you have, well, n input, and then if you have q outputs, okay, or something else, whatever you consider is a value, then the combination is your technology set. Now, the distance function, if you are thinking of directional distance function, is basically the maximum you can translate your input and output vector by in a given direction. And that direction is what's given here as GQ and GX, okay? And I just gave you an example a moment ago where these were 1 and -1. So once you choose a direction, and if you maximize that direction, that distance is your directional distance function value. Now, what do we know about the directional distance function here? Well, it's giving you the maximal number of units that you can translate your input-output vector along a given direction. So if I go back to that example I had, and if I have a point here, let's say F, and if my direction vector is 1 and -1, what I am saying is what's the maximal distance by which I can go in terms of reduction to input and increase in output. Well, I am talking about the length of this vector. If my vector, the length of that arc, if my vector is 1 and 1, then the length of this is going to be my theta. Okay, that's my distance function value. So what happens if my distance function value, let's say Gx is -1 and Gy is 1, that's my direction. What happens if this is 2? What am I saying? Well, what I am saying is to the input values I had here, F, if in F I had an input value of Xf and Yf, what it's saying is, well, I could reduce my input, let's go step by step, by 2 times 1. 1 is Ugx, okay, remember that. And this is your theta. And I could have increased my output by 2 times 1. Again, that's the theta, that's Ugy. That's what you are saying. So basically you are saying, well, looking at the point, observe point F and the frontier, it's clear if you go in the direction that's chosen, you could have reduced your inputs by 2 while simultaneously increasing your output by 2. That's all it's saying. And in other words, what is this? If the price of X is 3 and the price of Y is 5, what is it telling me about profit? Well, I could have increased my profit by what?
4.
Why 4?
because the quantity of X is 2 and Y quantity is 2, 5, 10, 3 to 6.
I could have reduced my inputs, not increased them by 2. So you are increasing revenue and reducing cost at the same time, right?
Yeah,
Would it be 6
6 minus 10.
Your revenue is going by 2 times 5, okay?
Yeah, 5, yeah, 10.
Revenue is plus 2 times
10.
5, 10. Okay,
And
change in revenue. What's the change in cost? Minus 2 times 3, that's minus 6. So the profit should be increasing by 16.
okay.
The profit should be increasing by 16. So in fact, this is a good example because you can see there that the directional distance function very easily translates into change in profit. So in a way, the directional distance function, if the directional distance function value is theta, it's telling you, well, you could have achieved an increase in output that's equivalent to theta times gy, and you could have achieved a decrease in cost that's equivalent to theta times gx. Well, then the change in revenue would be the price of y times theta times gy, and the change in cost would be the price of x times theta times gx. And the change in profit would be theta times pygy plus pxgy plus, so this is chosen vector, and this is the market prices. So you know this number, and if you know that number, the directional distance function tells you by how much your profit increases. And that increase is a product of the distance function value and the value of this quantity. So it can be translated into profit very easily. Just like you can translate input distance function value changes into cost, the reductions, and output distance function values into revenue.
Effectively,
yeah.
is that distance not necessarily optimal? Because if we've got other points, the direction already has to be set. So say there was another point there and it was not optimal, we still have to use that same direction though, don't we? But as you were saying before.
Yeah. So what you are saying is, well, for some points, it would have been more profitable to go a different way, right?
Yeah.
That's true, but you are measuring technical efficiency and you want a consistent yardstick. So to have a consistent yardstick, so if you want to know what the efficiency means, then you have to keep the direction fixed. But you are right. If you're interested in increasing profits, then you should be choosing a different direction. But what will happen is that comes as a form of allocative efficiency. So when you think of your profit efficiency, there is going to be not just the technical, there is going to also be the allocative. But in this case, what you are doing is, suppose you didn't have prices, you just had quantities, or even if you had prices, you wanted a comparable measure of technical efficiency. And that comparable measure is going to be how much more in terms of this direction you could have improved your input-output combination. So it's tempting to think, well, there is a better direction for this point, but then that defeats the whole purpose of having a measure of efficiency, because the measure of efficiency would have different meanings for different observations. That's what would happen, because if you start using different directions, then you have an idea of the prices. And if I have this, what's the best way to move F? Well, we know from what we know about production functions, well, that should be at the point where the isoprofit line touch the production frontier. So in this case, if I am maximizing profit, it should be going this way. No, cannot go that way. Hold on. I have to limit myself. I am being silly. We have to limit ourselves here. So if I am thinking of profit maximization, if I go that way, that means I have to increase my inputs as well. So I don't want to do that. I don't want to go full maximization. Let me draw a more convenient one. Let's say the optimal, because we are talking about technical stuff. We are not talking about is here. So this would be the most profitable. But if I do that, then I am taking prices into account. But if I don't do that and instead end up going into here because that's a direction, well, when I think of allocative efficiency, then the difference, so if I draw my let me use a different color again. So what you would have is this idea of, okay, the movement from here to here is your technical efficiency. So in terms of profits from here to the middle line is technical efficiency, and then the last line is your allocative efficiency. So that's the concept here. So you are measuring technical efficiency in comparable units, but your allocative efficiency is still out there. And without prices, you wouldn't even know anyway that you should have come here. There is no, you cannot know that you should have come here instead of being here, or instead of being here. So that's what many people wonder is, well, why can't we just use a more convenient direction? You cannot. You cannot, because you are looking for a yardstick that you can compare across points, and that yardstick has to stay the same. If you change that yardstick, then you are thinking about something else, which is overall efficiency, but we are talking about technical efficiency. So the overall efficiency is different because we know, let's keep it smooth here. So if I have an ISO profit line, well, the optimal input-output combination is this. But then the movement from here to here is my overall inefficiency, both technical and allocative. But if I break this down as a movement to here and then a movement to there, that's technical, and the second movement is allocative efficiency. But there is many different ways to do that, because I could have come here, which means I would have a different breakdown. So I could have gone in there, which means most of the movement is covered by technical efficiency, and there is little room for allocative efficiency because the technical efficient point is close to the optimal, profit optimal point. But these are arbitrary divisions. If you want a consistent way of measuring technical efficiency, you need to have the yardstick. And the benefit of having the same yardstick is, if I have a point F and the theta for point F is, well, 2, and I have a point G and the theta is 1, I can add up these efficiencies to know overall aggregate efficiency. And that's a special feature of the directional distance function, because these two things mean the same. The directions are the same. So the first one is saying, well, you could have increased your output and reduced your inputs by this. And the second one is saying you could have done that, but only once, one step. So if I combine them, because these directions are constant, I can sum them up. So one thing that the directional distance function allows you to do that the other distance functions don't is you can come up with an aggregate measure of inefficiency. So I could say, because the farms in the Kataning region are inefficient, we are losing so much per year in terms of profits, because I can add up all their inefficiencies. Whereas with radial distance functions, I can only say on average, we could have increased revenue by 20% or 10%. Or if I am using an input-oriented one, I could say on average, I could reduce cost by 15 or 20%. But I don't have a measure of aggregate inefficiency. Whereas in this case, because the direction is the same, the distance is measured using the same yardstick, which is the vector gy, gx, I can always lump them. And as we saw earlier, that actually translates into profit. So if I add directional distance function values for all the farmers or the producers, this is going to give me my aggregate gain from improvement in efficiency. So the yardstick has to stay the same. Is this clear? If you have an isoquant, point A, point B, the input distance function, it's always going this way, this way. So the direction depends on your starting point, because it's always pointing to the same direction as a scaling down, but you end up at different points. points. If you had been using a directional one and the direction said you go this way, then that one would have to come in a parallel line, which in this case seems to coincide by accident with a radial, but they have to be same. And if you use a different direction, which says they should go this way, well, that one has to go that way as well, parallel. That way, you have the same yardstick. You can translate the distance into cost when you have multiple things, but that's not the only thing. On the output side, because you would have a similar story, although we cannot draw everything in one, then you would have a direction here, a direction here, and I can combine this direction in revenue with the direction in cost, and that with that, and have meaningful measures of efficiency that I can translate into profit change. Okay, we'll have more on this. So I think the purpose in this lecture is to just slowly introduce you into the concepts without using the full-on definition of what these are and so on, because it's very easy to explain using curves what these things are and why they are different and why it makes sense to use the same direction and so on. But it does appear wasteful to not be heading for the most profitable point. No, this is technical efficiency, so that's where we are. Okay, so in a directional distance function, so sometimes you can have a directional vector only for just inputs and not outputs. That's important to remember. This is a special case. So what does that mean? Well, if you have one input and then you have a direction for only x, then it's the same as radial because there is only one way to go, but that's not true, as I was just showing you in the previous slide. Where did it go? If you have more than one input, there isn't a unique direction. There can be different directions. The red, the blue, and so on. So in some cases, your interest might be on a direction for one subset. So in the class and was asking the question earlier is working on soil quality indicators, and his interest is in the soil quality vector. So your direction in that case is for soil quality indicators only, because that's what you would be adjusting. So instead of GQ here, you would have G for soil quality S. So you can have your direction applied to a subset. This is good to remember. So in this case, it's only for Q because Gx is set to 0. So you leave the X vector as it is. So it's a partial translation. Now, this isn't easy to draw, but you can imagine you have 3 dimensions, let's say 1 output, 2 inputs, or 2 outputs and 1 input. And for any given point under that surface, because that would be a surface of some kind, what you are doing is you are measuring distance by moving. So if I had, my drawing might be bad here, x1, and I had y1, y2. So let's say I have some kind of a dome, like I'm not good at drawing this, but then I have a point under it. So when I'm thinking about approaching the surface, well, if my gx vector is 0, I'm going to keep x the same, and I will have just a direction for gy, which might be 1 and 1. Because my gx is 0, I will think in terms of moving from a point to the surface in such a way that I increase both outputs, okay? So up and towards y1, okay? You can imagine it because my drawing is not good. I am not helpful here. So the point is directional distance functions have vectors. Those vectors translate the variables of interest. The variables of interest normally are classified into inputs and outputs. So you could have directions for inputs and outputs. And those directions, as long as they are consistent between observations, can be different for inputs and outputs, or even for individual inputs, they can be different. But they have to stay the same across all observations. So if I have 3 outputs, 3 inputs, and I need a g vector, gy, gx, I can have a vector which says 1, 1, 1, minus 1, minus 1, minus 1, or I could say, well, I am interested in putting more weight on output 1 and more weight on reductions in input 1. I could have that. There is nothing preventing me from doing this. I still have the same yardstick, as long as I apply this to all observations. This is fine. I can also, as you can see, I can also choose to have gy. Well, I don't want to translate in output 1. I will just keep a translation on 2 and 3. And X, I could say, well, I am going to not translate input 3. That's a valid direction. As long as you use the same yardstick, the same direction for all your efficiency measurement, that's fine. So you can do these things. And of course, the quality indicator I mentioned, well, it translates only outputs. This is from a 0 vector, but Gx is equal to a 0 vector. That's 0 vector. Okay, so I'm not interested in translating outputs. So there is a lot of flexibility in that. So what this is doing is if I had an isocount and if I have a Gx which says I am not interested in translating output 2, and if I have a point A, which way am I going now? Well, the translation keeps input 2 same, so I'm going to be heading this way. That's my direction. But if you are wondering why is this all? So a common direction is 1, 1, 1, and a common direction is -1, -1. That's after you scale your y variables by their mean values and your x variables by their mean values. It's commonly used. What that means is your direction is your sample mean values. Okay, so efficiency gets measured in terms of the average value. So that's very convenient. There is a paper by one of my PhD students from 2017, Robertson. That's what he does. If your distance function is 0.5, then it's telling you could have increased your output by half of the sample value for output and reduced your inputs by half of the sample values for inputs. And that's easy for people to understand. Okay, so if you see this formulation after translation, that's really convenient. That's natural in a way if you identify the sample mean as a good way of measuring things, but there is no wrong or right way to define your distance. It has to make sense and it has to be meaningful. Now, there are different indices. We'll come back to this. There is Malmquist indices that are based on radial distance functions. There are Luenberg indexes that are based on directional distance functions. And as I was saying, the directional distance function provides a numerator that's constant. It doesn't mix yardsticks. So coming back to your question, if you choose different directions, that would mean mixing different yardsticks to measure efficiency. Normally, the choice of the direction is a mean vector. If you have no other more sensible or defensible choices, you choose the mean direction vector. That's what I was just saying. And if you scale your inputs and outputs or whatever you are translating by the mean values, then you can use the unit vector. The unit vector is vector of ones as your direction. So how do we construct the frontier? Well, we know quite a lot about this by now. Obviously, there is DA. Whatever limitations it has, DA being deterministic, sensitive to outliers, and also probably the tightest inner bound, as I said earlier. But it's easy to implement. You don't have to make effort to incorporate multiple outputs. And you can calculate radial or directional distance functions very easily. So DA is commonly used, and you can use SFA. So in some cases, you can also use SFA. Well, it's MLE, but you can also use Bayesian methods. Can be more difficult to implement, but it's doable. So now your production function, your stochastic frontier, is this, but it has got only one output. If you have a distance function, you have more than one output. So how do you use, say, SFA? It's possible to use SFA. Again, check the paper by Kataz. What he did is he translates this into something that he can estimate using SFA. So we'll come back to that one. How do you translate it? Using its linear homogeneity. So last week we were talking about the cost function being linear homogeneous in prices and profit functions being linear homogeneous in, well, all prices, output and input, while the cost is just in input prices. Distance functions like radial distance functions have homogeneity properties. Input distance function in terms of inputs and output in terms of outputs. You can use them to translate. So that's something that we'll attempt later. But you have these choices. It's possible to estimate. You can also use other methods like mathematical programming to estimate things. So for example, if I want a deterministic frontier, I could use mathematical programming. I don't care about errors. So it's the equivalent of the DA, but except in the mathematical programming, actually, I am estimating a smooth function, but using mathematical programming. So how does that work? Well, I just make sure that my distance function value, if it's input distance function value, is always greater than or equal to 1, which means my data points are always inside the feasible space. We'll come back to this. And I can estimate the translog. I can write this at translog. So my early study on the Canadian pulp and paper, and also papers that were done before me, or a couple. One was by far 1993, and there was another Coggins and Swinton 96 using output distance function. I used input distance function. There were only a few papers in the 90s. Those things estimate the function as translog, but without using econometrics as constraint minimization of a deviation from a frontier. So that's the equivalent of the basically a DA type, but it's parametric. So you will see that in a paper that's available, published in 2000 in June. So that's all I have for directions. I think the main thing is if you have bad outputs, sometimes it makes sense to include them for efficiency and productivity measurement to be accurate, but also shadow prices and for policy. How much does it cost to reduce pollution? So that's one big motivation. If you have bad outputs, you need multi-output models. And those multi-output models could be different things. They could be DA models, and nothing changes here compared to when you don't have bad outputs. You just use DA, except you need to be careful about monotonicity, or you could use distance functions. And we have looked at 3 types of distance functions. One is input distance. Okay, so we didn't look at the function in detail, but the idea of the input-oriented or input direction, output distance or output direction. We have also looked at directional, and this is relatively new, so it can be here a bit strange to people, but it needs a direction, a common direction, and that common direction has to stay the same. It has a profit interpretation of efficiency change. This is related to cost saving. This is related to revenue enhancement. So that's what we have. And then when it comes to estimating them beyond defining what they are and so on, then you can use different frontiers. So you can have DA, SFA, or deterministic frontiers, but over time these are becoming less and less important. So because now you can do that. A lot of the work I do is to use SFA, but using Bayesian methods. Why Bayesian? Because I can then maintain theoretical properties very easily. So basically what I'm doing is getting the benefits of mathematical programming, which imposes very easily monotonicity and so on, but combining it with the stochastic frontier stuff. So that way you can make sure that your functions are monotonic and they have the right curvature. So input distance functions have to be concave, like for cost functions, and output distance functions have to be convex, like profit functions. And those things are important to impose, especially when you are after shadow prices. So in normal analysis, if you estimate a cost function or profit function, mostly people don't worry about the monotonic properties because they can ignore them. They look at the coefficients, elastic values, and so on. Even if the elastic values are negative or the wrong sign for some observations, they can skip that and look at the overall picture. But when you are after shadow prices and you have been hired to come up with estimates of carbon cost reduction, well, you cannot say, well, some of my cost estimates are the opposite sign. Well, that won't fly. So you need stronger methods. You need to take more control of what's happening and not leave things to chance. So that's a prime motivation, because you cannot have a paper which says I am estimating the cost of pollution reduction, but by the way, on average, the cost of pollution reduction for carbon is $12, but I also get -50 for some of the observations. That is not a proper model. So there's a very strong reason why we go to all the trouble of using Bayesian methods to impose monotonicity constraints on them and other constraints as well. So that's all I have.